All right, Gen Chem kids, we are going to add yet another layer to this whole molecular forces thing. So we're now going to talk about the forces of attraction in between different molecules. So we've spent the last week or two discussing the intramolecular bond. Intra means within. Can't spell. Within. So the bond within molecules. So we've talked about covalent bonds, we've talked about ionic bonds. Okay? So the intramolecular bond is the bond that holds atoms together within a molecule. For instance, we talked about the covalent bonds that hold hydrogen atoms to oxygen in a water molecule. And they are an example of intramolecular bonds because they are within the molecule. Okay, so let me just do a little Lewis structure of water here. By now you should see that water is a bent molecule, and these bonds here are covalent polar, right? And they are intra because they are within that molecule. Okay, or the ionic bond that holds sodium and chloride ions together. Sodium is a +1, chloride is a -1. So opposites attract, right? Positives attract negatives. So when we make table salt or sodium chloride, we will have NaCl. +1 plus -1 equals 0, right? So that's the ratio we have. So here we go. We're going to talk about the differences between some of these bonds and do some compare and contrast. So ionic bonds, here's a model. We usually think of them as just NaCl, but in reality, it's not just NaCl. We get a crystalline structure where they're all kind of interspread like this. And that's why when you pour salt out on your hand, you get those little cubic crystals in your hand, because salt isn't just one sodium and one chloride. It's a crystal all together of positives and negatives all in this lattice together. We have the basis of attraction. We have the cations, the positives, attracting with the negatives. We have our sodium chloride. Let's give you an example of some of the properties of ionic compounds. So ionic compounds have really, really strong bonds. And they're brittle. If you've ever taken a crystal, you know that you can shatter it. It doesn't bend, it doesn't give, it shatters. So they're really brittle. They have high melting points and really high boiling points. Okay? Now, covalent, we're sharing these electrons between these two atoms, okay? The positive nuclei attract the electrons between the two nuclei, okay? Our example here is hydrogen. Now, these are relatively weaker bonds than ionic bonds, so we have lower, I can't spell today, we have lower melting points and boiling points. In fact, most of our covalent stuff we can actually melt pretty readily. Think of things that could be solid but we can melt easily, like butter, right? I throw some butter in the pan and it's going to melt. Or oil is already a liquid at room temperature because it has a weaker bond structure than ionic bonds. And then we have metallic bonds, where we have the metal cation and the valence electrons. Those valence electrons, those outermost electrons, can move freely between everything. That's why these can conduct electricity. That's why metals conduct electricity. This is also why they conduct heat very well. That's why we make our pans, our pots and pans out of metal, because it can conduct heat very well. And because these electrons and these cations are free to move back and forth against each other, these are what we call malleable. If I can spell it, malleable, which means that I can pound it, I can shape it, I can bend it, I can twist it. That's why we make so many things out of metal. I can make so many shapes, and I can do lots of things with it. It's also ductile, which means I can make wires out of it. Okay? So, the thing I want to talk about, though, is bonds that hold molecules together with each other. So what about those bonds, for example, that hold water molecules together to form a liquid or solid? To make it liquid, those molecules have to stick next to each other. They can still move around each other, but they've got to stick right next to each other. And to make a solid, they've got to be in a crystalline structure so that they still move, they still vibrate, but not very much. So these type of bonds are what we call intermolecular bonds. So inter is in between. So in between molecules. So, for example, we are going to talk about 3 different intermolecular bonds and 3 different ways that molecules interact with each other. Okay? The first one is called dispersion forces. The real name is called London dispersion forces. Okay? Recall that when we did oxygen, our Lewis structure for oxygen was this, right? We had 2 lone pairs on each oxygen and a double bond. And we said that this was nonpolar because oxygen has the same electronegativity as the other oxygen. So those electrons are going to be shared evenly, right? Those electrons are evenly distributed between equally electronegative oxygen atoms. But under the right conditions, however, oxygen molecules can be compressed into a liquid. Okay? Yes, liquid oxygen. For oxygen to condense, there must be some force of attraction between the molecules. So what is that force? The force of attraction between those oxygen molecules is called a dispersion force or a London dispersion force. Dispersion forces are weak. They are not very strong. And they result from temporary shifts, and they are not permanent. They are temporary shifts in the density of electrons in the electron clouds. Remember, the electrons are kind of moving around all that atom, right? So are they always going to be evenly distributed around that atom? No. Okay? Sometimes for just a split second, more electrons are going to be on one side of the atom than the other. So that means that this side of the atom for just a split second is going to be negatively charged. And this side of the atom for just a split second is going to be positively charged. So this one is for a split second positively charged. Isn't it going to draw the electrons of the neighboring atom or the neighboring molecule? So that side becomes negatively charged for just a split second? Yeah, it will. And we get this chain reaction through all the molecules that are next to each other, and eventually we get enough cohesive forces going on that we can condense things, or maybe even make them a solid. Okay? So dispersion forces are called London dispersion forces. Okay? After the German-American physicist who first described them, Fritz London. There was also another Dutch scientist that did this at the same time. His name was van der Waal. So sometimes people will call them van der Waals forces, and some people will call them London dispersion forces. I am lazy, I call them LDFs. So when we talk about this, I usually talk about LDFs. Okay? All right? And they're temporary. These poles are not permanent because the electrons are constantly moving. Okay? So these are temporary dipoles. Dispersion forces exist between all particles. Dispersion forces are weak for small particles, and these forces have an increasing effect as the number of electrons involved increases. So more electrons, the more the electron cloud can be manipulated, right? Thus, dispersion forces tend to become stronger. As the size of the particles increase. Okay, for example, fluorine, chlorine, and bromine. Let's get out my periodic table here. Let's see, periodic table. Here we go. So if I look at my halogens, fluorine, chlorine, bromine, iodine. Okay, these guys. We're talking about these guys. All nonmetals, by the way. Okay? So if I talk about these guys, fluorine, this is going down the periodic table. So fluorine is our lightest one, then chlorine, bromine's a little bit bigger, iodine is the biggest, and then the tacitocene at the bottom. They all exist as diatomic molecules. That just means they come in groups of two. So for example, I would have chlorine as Cl2 or fluorine as F2. They come in groups of two, okay? Recall the number of nonvalence electrons increases from fluorine to chlorine to bromine, right? We're just adding on another layer of electrons each time we go down. Because the larger halogen molecules have more electrons, right? Because they have more electrons, there can be a greater difference in the positive and negative regions of those temporary dipoles, thus stronger dispersion forces. This difference in dispersion forces explains why fluorine and chlorine are gases. So fluorine and chlorine are gases at room temperature. Okay? Bromine, next one down, is a liquid. It's an orange liquid at room temperature. And then if I look at iodine at room temperature, it is a solid. It is a very dark purple, almost black crystalline solid. Okay? All right, so the more electrons I have, the more dispersion forces can act. All right, dipole. Polar molecules contain permanent dipoles. So these aren't temporary anymore. These are permanent because they are polar molecules. That is, some regions of a polar molecule are always partially negative, and some regions of the molecule are always partially positive. These attractions between oppositely charged regions of polar molecules are called dipole-dipole effects or forces. Neighboring polar molecules orient themselves so that opposite charged regions align. So let me give you an example here. So we're going to look at hydrogen fluoride or hydrogen chloride. So if I look at the electronegativity of hydrogen, I have an electronegativity of 2.1. And if I look at the electronegativity of chlorine, I have electronegativity of about 3.2. Okay, so this gives me a difference of about 1.1. Okay, hydrogen is not nearly as electronegative as chlorine. So hydrogen gets a partial positive charge because the electron from hydrogen is mostly drawn towards that chlorine, right? That extra electron gives that chlorine a partial negative charge. So guess what? All of the hydrogen chloride molecules are the same. So if this chloride region is partially negative, the next molecule is going to orient the hydrogen towards this region with a little bit of an attractive bond here, because opposites attract. So if I have a whole bunch of these molecules all together, they would line up like this. We would actually have molecules lining up and creating some kind of a big mass molecular structure because of these different positive and negative charges. That helps these molecules get closer to each other, which means that they are going to be liquids and solids at lower temperatures. Okay? All right. And last but not least, we have hydrogen bonding, which is a very special type of dipole-dipole thing. Okay? It's a very special case. Now, the thing about hydrogen bonding, it doesn't mean that you just have hydrogen in the molecule. No. Hydrogen has to be bonded to a nitrogen, an oxygen, or a fluorine. So, for example, only hydrogen fluoride, only that bond, hydrogen and oxygen, or hydrogen and nitrogen. Yes, those bonds can be part of a bigger molecule, but you have to have hydrogen with a fluorine, hydrogen with an oxygen, or hydrogen with a nitrogen. Hydrogen bonding does not mean that you just have hydrogen in there, okay? It has to be fluorine, oxygen, or nitrogen bonded to a hydrogen. Okay? So, for example, we've got water here. Now, because fluorine, oxygen, and nitrogen are so small and are so electronegative, what they do is they essentially strip that electron away from the hydrogen. So, for example, let's move this. The electronegativity of fluorine is 4. Oxygen's 3.5 and nitrogen's 3.0. Hydrogen is 2.1. So this gives us a 1.9 difference here. This gives us a 1.4 difference here. And this gives us a 0.9 difference here, which are pretty big differences. Okay? So what it essentially does is we take that hydrogen electron off and we give it to the fluorine, the oxygen, or nitrogen. So fluorine has a negative, almost a whole entire -1 charge, or oxygen has a whole entire -1 charge. Nitrogen almost has a whole entire -1 charge. And hydrogen almost has a whole entire +1 charge. So this is almost acting like an ionic bond, but not quite. Okay? So that means the hydrogen regions on water are really, really positive. And it means this oxygen region is really, really negative. So the hydrogen regions of one molecule will line up pretty well to be with an oxygen region on another molecule, because remember, opposites attract. So we get hydrogen bonding between different molecules where we have regions of high positive areas and a region of high negative areas. And this is why water is a liquid at room temperature and not a gas. And this is why water expands when it freezes instead of contracts. All of the really fun properties of water are all due to hydrogen bonding. Okay? Basically, biology would not happen without hydrogen bonding. So this intermolecular force of hydrogen bonding is why life exists. Honestly, truly. Okay? All right, let's compare water with some other molecules of the same mass. Okay? So water has a molar mass of 18, methane is about 16, and ammonia is 17. Notice methane's boiling point is negative 161.5 degrees Celsius. So it is definitely a gas at room temperature. Room temperature Celsius is about 20 degrees. Okay? So methane has been a gas for the last 180 degrees. Okay? Ammonia has been a gas for about the last 50 degrees. Okay? But water's boiling point is 100 degrees Celsius. That's why it's liquid at room temperature, because of these hydrogen bonds that we have between the oxygen and the hydrogen, and the attractive forces that it can create between the oxygen molecules, or the oxygen and hydrogen in the water molecules. Sorry, I misspoke. So let's look at these molecules. Which molecules listed below can form hydrogen bonds? Now remember, hydrogen bonds are just hydrogens with fluorines, hydrogens with oxygens, or hydrogens with nitrogens. Okay? So let's look at A. I've got hydrogen with hydrogen. Is it with any of these? No. So that cannot make a hydrogen bond. Okay? All right, how about H2S? Do we have a hydrogen bound to a fluorine, an oxygen, or a nitrogen? Nope. Let's draw the Lewis structures really quick for these. So there's hydrogen, hydrogen sulfide, dihydrogen sulfide. I'm going to put in the lone pairs here so that you can see why I'm drawing it bent. Hydrogen chloride, okay, and hydrogen fluoride. Okay, any hydrogen bonds going on there? Hopefully you saw this one, hydrogen fluoride. It's the only one that can create hydrogen bonding. All the rest of them, no, not hydrogen bonding. So I want to draw molecules of two water molecules and show the hydrogen bonding between the two. So if I draw a water molecule, and I'm going to draw another water molecule nearby. Remember, hydrogen bonding takes the positive area from one molecule and bonds it to a negative area of another molecule. So where would that bonding be? Remember, the hydrogens are positive, right? And the oxygens are negative. So our hydrogen bond, I'm going to draw this in pink as dots, is going to be right there between the hydrogen on this molecule and the oxygen on this molecule. So it's going to push these two molecules close together. How about two ammonia molecules? Same thing. The negative area is going to be attracted to the positive area on another molecule. So if I have ammonia and it is a trigonal pyramidal shape, it's going to be attracted to the hydrogen. The nitrogen is going to be attracted to the hydrogen on another molecule. So I'm going to put these in as dots. Yep, if I can put them in as green. So that is my hydrogen bond right there. Why won't it let me put hydrogen bond in there? Okay. All right. What about between a water molecule and an ammonia molecule? So if I have a water molecule, let's start over. Okay. Water and ammonia. So where are they going to be attracted? Remember, the positive area of one is going to be attracted to the negative area of another. So would I have a hydrogen bond there? Yeah, that would be an H bond or a hydrogen bond. Could I also flip it around? You betcha. I could definitely flip it around. So I could do a nitrogen or an ammonia, and I could have it be attracted this way to a water. Right there. That could also be an H bond. Okay? So we have multiple ways that we can create hydrogen bonding. Now remember, hydrogen bonding is hydrogen with a fluorine, an oxygen, or hydrogen with a fluorine, an oxygen, or a nitrogen. Okay, network covalent bonds are actually pretty strong too, but they are very rare. So if I have a network covalent, that means I have a really big structure of covalent bonds. We have diamonds where carbon is tetrahedrally bound to other carbons. That creates a very strong, very vast network. That's why diamonds are so strong, such a high melting point. They are the strongest, hardest thing on the earth. We can have a Buckminster fullerene ball where we have carbons that are sometimes tetrahedrally bound and sometimes trigonal pyramidally bound. Okay, so these Buckminster fullerene balls are very, very slippery. And because they're very, very slippery and very small, a lot of times they're used as lubricants for really hot industrialized processes that need to happen at really high temperatures, where oil and the normal lubricants would just be burned. Okay. And then we have graphite. Notice the graphite. This is the stuff that is in your pencil. Graphite is sheets. So I've got a sheet of carbon right here. And the carbon is trigonally pyramidally bound to each other. And because it's in sheets, that when I press my pencil to the paper, these sheets come off onto the paper. So there's strong bonds within each sheet, but the bonds in between these sheets, so in between these different layers, are just London dispersion forces. They're not very strong because they're just LDFs. And because the LDFs are not nearly as strong as the network covalent, the sheets of lead, when you press your lead pencil to the paper, the sheets will come off, and that's how you write with your pencil. Okay? All right. So have a great time. I have some questions for you on Canvas that deal with LDFs and looking at different molecules and telling me what kind of LDFs they are. So I want to have you have some practice with that. So let's go back for these ones back here. So this hydrogen, hydrogen is totally nonpolar, right? Right here, HF. So if it's not nonpolar, the only type of intermolecular forces that we have for hydrogen are London dispersion forces, LDFs. So hydrogen is only going to have LDFs. Let's look at this hydrogen disulfide or dihydrogen sulfide. Don't I have some dipoles going on here where actually it's going to be the opposite way? The hydrogen is going to be less electronegative than the sulfur. I also have this big area of electrons up here. So this is going to be polar. So this is going to be dipole, dipole. And chlorine is way more electronegative than hydrogen. So I have a dipole here. So that's also going to be dipole, dipole. And then hydrogen fluoride, hydrogen bonding, because I've got hydrogen bound to a fluorine. All right, so good luck. Remember to use your notes for your assignment in Canvas, and we'll see you later. Bye.